Welcome to The Explainer. Today, we're putting on our AI historian hats to uncover the hidden mechanics of sequence modeling. You know, when you type a prompt into GPT-4 or ask a diffusion model to generate an image, it feels like absolute magic. But right beneath that magic lies a mathematical framework that is over a century old. We're going to explore the mathematical DNA of modern AI. We'll look at the cage we built to understand the future and why, ultimately, we had to break it.
To see where AI is headed, we've got to jump all the way back to late 19th century Russia. Picture the mathematician Andrei Markov. At a time when probability theory was mostly just about independent events, like flipping a coin, Markov had a much bolder idea. He wanted to prove that predictability applied to dependent events, specifically analyzing the sequence of vowels and consonants in Russian poetry. He wanted to model a future that depended entirely on the past. Honestly, this was the first time we dared to model the future.
Part 1. Modeling the Unknown Future, the Birth of Algorithmic Sequence Modeling.
So, Markov faced an immediate, towering problem. Calculating the future based on an infinitely growing past is just computationally impossible. You literally can't calculate the future if you're dragged down by measuring the weight of the entire past. So, how do you solve it? He invented a mathematical constraint, which we now call the Markov Property. It's the radical assumption that the future depends only on the present state. It completely 100% forgets the past. This clever trick drops the complexity from an impossible, exponentially growing distribution down to a simple, computable product of conditional probabilities. It was a brilliant piece of engineering necessity.
Moving into Section 2, the memoryless frog, state transitions as a game.
To really grasp this, I want you to imagine these mathematical state transitions not as abstract math equations, but as a physical board game. Imagine a stylized, geometric frog sitting on a lilypad. That lilypad is our current state. Here's how the game works. Step 1. Our blindfolded frog just sits on the pad. Step 2. Pop. A rigged dice appears over its head and rolls. The weighting of that dice is dictated entirely by that specific lilypad. Step 3. Based on the roll, the frog jumps to a neighboring pad. And this brilliantly illustrates the core concept here. The frog has absolutely zero memory of how it got there. Its entire universe of decision-making is restricted to the single pad beneath its feet.
Let's ground this in something concrete, like a classic two-state weather model. We can organize our frog's jumping rules into a simple grid. If it's sunny today, there's an 80% chance it'll be sunny tomorrow, and a 20% chance it'll be rainy. Which sounds fine until you realize this poor frog is trapped in a perpetual weather simulation. If it's rainy today, it's a 50-50 split for tomorrow. If you mop this out, all the possible jumps leaving a single state have to add up to exactly 1.0, or 100%. When we organize these probabilities together, we form what is called a stochastic matrix.
Focus on that 0.8 for a second. That represents the 80% probability of staying sunny if it is already sunny. That is the rigged dice rule popping up over our frog's head, dictating its very next jump. This transition matrix isn't just a table of data. It is the absolute, unbreakable rulebook of the universe this frog lives in.
Now, if we hit fast forward and simulate our memoryless frog taking infinite jumps, something truly beautiful happens. We reach a predictable end state known as the stationary distribution. Regardless of whether the frog started out on a sunny day or a rainy day, over infinite time it will predictably spend exactly 5/7, or about 71.4% of its time, in the sun. Think about that for a second. From pure, random, memoryless jumps, rigorous mathematical predictability emerges.
Section 3. The Matrix and the Machine, Scaling to the Modern Era.
So how do we get from a solitary hopping frog to the massive GPU clusters running AI today? Because, trust me, we aren't using clunky if-else statements to simulate a single frog jumping around. Here is the computational magic. If we want to find out where the frog will be in 100 steps, we don't sit around watching a frog jump 100 times. Instead, we use linear algebra. By raising our transition matrix to the 100th power and multiplying it by our starting state, we instantly calculate the future state distribution. Matrix exponentiation effectively lets us time travel mathematically.
And here is the massive engineering aha moment. We aren't using linear algebra and matrices just because the math is elegant. We use them so we can batch process. We use matrix multiplication so we can calculate 10,000 frogs jumping simultaneously.
If you try writing a basic Python for loop to update 10,000 agents in a simulation, it takes milliseconds per step. In computing time, that is agonizingly slow.
But by swapping that for matrix operations, like torch.matmat, we push that batching directly to GPU tensor cores. We can update all 10,000 frogs in microseconds. This massive, high-speed parallelization is the absolute bedrock of simulating thousands of environments at once in modern reinforcement learning and Bayesian inference.
Which brings us to Section 4, breaking the Markov cage, the fatal flaw in language modeling.
Because for all its brilliance, the Markov chain has a fatal flaw when it comes to the complexity of human language. It's called the curse of dimensionality. If you try to apply a Markov chain to a language model with a standard 50,000-word vocabulary, your state space just explodes. Your transition matrix suddenly requires 2.5 billion parameters. It literally takes 10 gigabytes of memory just to store the matrix. It creates this massive, exponentially growing bottleneck that grinds everything to a halt. This instant explosion is exactly why explicit Markov chains had to be completely abandoned for text generation.
But beyond the raw compute cost, the logic itself is flawed for text. Think about the structural difference here. A Markov chain is essentially a localized series of connected memoryless boxes. But a transformer, the architecture running modern LLMs, is a global, full mesh web of attention lines. Why does language require global memory? Well, think of the sentence, "The animal didn't cross the street because it was tired." A memoryless Markov chain only looks at the localized word because and has absolutely zero idea what it refers to. A transformer looks back globally, checking the whole context, to know it means the animal from 10 words prior.
So, the dramatic realization is this. The Markov property is the cage we had to break to build modern AI. Modern large language models explicitly violate the Markov property. They achieve true comprehension not by forgetting the past, but by using self-attention to constantly evaluate the entire history of the sequence. But hey, let's be super clear. Markov isn't dead. We dumped it for language, sure, but it is still quietly powering massive chunks of modern tech. Diffusion models like DALL-E use explicit Markov chains in their forward noising process. We intentionally sacrifice the expressivity of a long-range model for the mathematical tractability of closed-form equations. It's also the backbone of reinforcement learning and even Google's original PageRank algorithm. We've gone from a 19th-century mathematician analyzing poetry to blindfolded frogs, right up to the massive GPU matrices of the Transformer era. We built a mathematical cage to make the universe computable, and then we broke that cage to make AI fluent, which leaves us with a final, pretty provocative thought. If sacrificing expressivity for tractability built the AI of today, what is the next mathematical cage we will need to break to reach artificial general intelligence? Thanks for joining me on this explainer. I hope this helped you see the math behind the magic. Keep learning, and I'll catch you next time.